All right, here we start.
Yeah, so
All right, okay, good afternoon. Thanks for coming to the Space Science Center seminar. Today's speaker is Dr. John Swoboda from MIT Haystack Observatory. He is working on several projects to set up sensor network around our region to study the solar eclipse. And he will tell us about those projects, and he also has some ideas on how UNH can contribute to those projects. Okay, let's take over.
Thank you. And I also want to just say thank you to Ningo again for taking myself and a couple of technicians from MIT Haystack around to do site surveys. Obviously, I have changed because it's a little muddy out there still. My talk today is going to just talk about the eclipse and various types of the eclipse, the effects it has in the ionospheric thermosphere, some new measurement methods. These new measurement methods are actually going to be kind of a combined sensor network. We have the Zephyr Media Wind Radar Network and the electromagnetic vector sensor ionospheric sounding MVSIS. These are two we call them HF sensors. They're HF radars. So HF is the band between 3 megahertz and 30 megahertz. That is just a standard electromagnetic frequency band. And we'll be sending out signals and also receiving them and using our vector sensors, which I'll explain a little bit further about their specialized type of antennas. And then our campaign for the 2024 Eclipse at Haystack, both our current operational sensors and the new radar deployment that we're doing. And also quick questions with Haystack. Is everyone here familiar with Haystack Observatory? So we're in Westford, Massachusetts. We are a department at MIT. We do share a site with MIT Lincoln Laboratory, but we are fully academic. We do research. We're always open to collaborate with people in UNH and other universities, and kind of share and work together to better understand the ionospheric, thermosphere, and atmospheric here. So first up, we're going to talk about the solar eclipse, effects of the solar eclipse, and also I'm going to be spending time kind of focusing on first the type of sensors we've used in the past. So sensors, the two I'm going to focus on are going to be the GPS TEC and the Incoherent scatter radar, and then I'm going to talk about how modeling of the eclipse and how that compares to observational results. And I'm using as a case study the 2017 Great American Solar Eclipse. Great American Solar Eclipse now there. So first off, the types of things we do at Haystack. So at Haystack, one of the things we have is our Millstone Hill ISR, where we have two large antennas, 46 meters and 68 meter antennas. The Incoherent scatter radar, what it's doing is it's you're essentially, if you guys are familiar with plasma physics, we're measuring the ion acoustic line and the electron line specifically. So what we're doing is we're sending out a pulse, and that is scattering off the electrons through lambda damping. You're actually able to see the ion acoustic modes coming in through the radar scatter, and from that we have a full physics-based model that is parameterized by electron density, plasma temperature, ion temperature, electron temperature, ion velocity, and the composition of the background ions. So for example, if you're in different parts of the ionosphere, if you're above around 250 kilometers, you're getting mostly O plus ions. Below that, you're getting NO 2 plus ions. And so you have to then adjust your fitting or your model based off of that. And this is just sort of a very basic idea of how we're measuring. We're looking at essentially a power spectral density, and from there deriving the plasma parameters from it. And so we're actually, the one thing, there's a lot of special aspects about the Millstone Hill ISR. We're actually the only Incoherent scatter radar in the continental US. Actually Arecibo was an Incoherent scatter radar. It was actually one of the first. But the other one within the United States is the AMISR system, the Advanced Modular Incoherent Scatter Systems, one in in Alaska and another in Resolute Bay, Canada, although right now the Resolute Bay one is offline. If you want to come and learn about Incoherent scatter radar, just stop by Haystack. So the other major type of sensor network we're using, and this one's actually more of a global or continental scale measurement, whereas the Incoherent scatter is much more a local measurement. You have a single remote sensor looking up into the sky and trying to pull in as much information as it can. With the other measurement I'm going to talk about is GPS TEC. And the total electron content, if you're familiar with that, you have your various GNSS satellites up there, the global navigation satellite systems. So we generally use both. We use GPS, Galileo. I believe we're starting to process BINU data, and I think GLONASS is in there, but I'm not certain at the moment. But the way we sort of measure this is that as your GPS signal travels from the satellite to your receiver, you have to correct for various things. One of the big things you have to correct for is the ionosphere. So if you have a dual frequency GPS, you can actually back out essentially how much plasma is in between you and your satellite that you're getting the signal from. You then sort of start to plot these essentially integrated plasma measurements over a map, and you can see all kinds of ionospheric phenomena. This year, I think there's a ton of ionization coming down from Canada and just increasing the electron density. So we use GPS TEC as sort of a kind of we use it as an integrated measurement of electron density, where we don't really have information about the altitude. So with Incoherent scatter radar, we get an altitude result measurement. With GPS TEC, we do not. And I'm calling it GPS TEC or GN. It should be GNSS TEC, but I've gotten to the mode of GPS TEC. I apologize. And so we're able to sort of then see large scale features over this. So I'm going to show some videos where you can kind of see very interesting wave modes come into the ionosphere and move through. So now that we're so these are kind of the two main measurement modalities I want to talk about, because that's where I can really show data from at the moment. And so we were able to run, so for the Eclipse in 2017, there was this big challenge thrown down to have various people try to study the effect of the eclipse on the ionosphere. And we're kind of starting, we're going to focus on things, we're going to focus mainly on electron density and how much electron density changes based off of the eclipse. And a couple of scientists, Joe Cuba and D. Drob in 2017 had made their simulation to show here's how much, the top is the electron density drop off around a specific point near eclipse totality. And then here's what the TEC would be, the integrated measurement. So they kind of did a global model of the ionosphere during the eclipse, and then they did some processing to see, okay, what's the TEC measurement going to be at this specific place in time. And so the idea is that you can take this and compare it to your measurements. And so that's what so this way we can understand how well we're able to how well these models can resolve and understand what's going on in the ionosphere in events such as a solar eclipse. It's a big change from where what's usually happening. So the few things that the model predicted, EUV reduction, about 50%. In the region, they predicted about 35% reduction in TEC. So I'm going to focus on that one right there, because again, it's easy to kind of show it's easy to show with our sensors that we have right now how these drops taking place, and be able to compare and contrast later on, like as we get better sensors, what else we can measure. But you had cooling about 800K of cooling in the upper ionosphere. We have reduction in ionospheric pressure, and then we should see continental size modification of the ionospheric conductance. It's a little harder to measure conductance, but there you can kind of back that out from the TEC. I think you can back some of it out from the TEC. But generally, when we're doing conductance, you need an increment scatter radar over a certain area to do that, because you want altitude resolved, and you have assumptions of how your beams are located. So this movie here just shows very quickly kind of the the sun as it moves through, and where totality is, and how much of the sun is during this eclipse in 2017. So that little tiny dot right there was totality. So that's when, again, the moon is completely in front of the sun. I'm just going to play that one more time. And it kind of started from Portland, Oregon, and kind of went down around South Carolina, Georgia, when it exited. I was actually in Wyoming when they did the eclipse. And the unfortunate part, I don't have slides of this, but I had a GPS sensor, and one thing I learned is never park next to truck stops when you're doing GPS. Truckers have GPS jammers generally, and they will knock out your sensor, your GPS, because they're being recorded by their companies, and there's a whole bunch of stuff going on. So yeah, just to keep that in mind. So if there's one thing you get from my talk, no GPS near a truck stop. But I think of the sea totality, it's amazing. Highly suggest it. And for the eclipse in April is 2024, I think Stowe, Vermont, and maybe in northern New Hampshire, you have totality. Weather might not be great in April in northern Vermont and New Hampshire, but go to a friend's house and kind of have backup plans is what I'm saying. Now when we're dealing with this sort of experiment, we want to understand what are the other factors here. So the first thing you're going to want to do is look at the KP index. During this time, and it was relatively the KP was relatively good on August 21st. It was a lower KP. Right after that, you had sort of a big jump in the KP index afterwards. So you do have more activity, but so this is generally, in terms of space weather from big solar events, this is relatively quiet, at least during the eclipse. So anything before the eclipse, you get a nice comparison. After, so when you look at what happens after, you're going to want to be careful, because again, KP jumped up quite high, so you might have some more space weather effects you'll have to try to filter out. But beforehand, one thing I'll be doing though is measuring, about a month before the eclipse and a month after the eclipse, so we can get kind of that nice sort of smooth line and figure out how things are changing over that time period. So,
I'm sorry, could you remember the exact date of the eclipse?
this was August 21st, 2017.
Okay.
Yeah, so day of
On the green period. here.
green is fully green, and then a little bit after you have a jump in the KP up to 6. So I just wanted to kind of say that this is it was relatively quiet space weather-wise. So at the Incoherent scatter radar, you can kind of see the difference between an eclipse day and an no eclipse day. This is the zenith antenna, so it's pointing directly up. Now we were, I believe, about 60% occulted, blocked at Haystack during the eclipse. And so you do see a very huge drop in the electron density between the UT 18 and UT 20, and so that's to be expected. We do have other, there are other aspects to look at this. There are also issues where, and I'll pick up a little bit more about this later, but the fitting of this data becomes kind of complicated. So when we fit parameters in Incoherent scatter radar, we make assumptions about the ion composition. Now, there could be ion composition can change at times. Generally, it stays pretty stable during the daylight hours, but with the eclipse, there could be some changing in the ion composition where the ion composition becomes much more important when you're trying to figure out electron temperature and ion temperature. Electron density is generally not that affected by that, but so this is just electron density to show that we do have a drop in the electron density around the time that we see it, and we're trying, and it's about, the drop is, we're seeing quite a precipitous drop from by about an order of 2 to 4. So we're losing a lot of ionosphere in here. So it does drop back quite a bit.
Sorry.
Yeah. So this does drop by about.
All the question at the end, or you don't mind being interrupted?
You can kind of, if you have a quick question, feel free. But you do see, we're losing, so we're losing something like in the factor of 40% of the ionosphere at this time. So the issue that Cuba did say, he was like, well, we're going to get up to about 35% loss. So again, it's sort of overshooting this already. We're seeing a greater loss in electron density. And I'm using electron density. It's very easy to see how these change. And then you can see ionosphere changes during the eclipse. Again, electron density and how we had this is our moving incurrent scatter antenna, the MISA. So this antenna right here, for those who can see me pointing at that. So that can move at 360 degrees. And we had that kind of doing these swaths along the where we would see the totality. And so so we're able to actually get some parts right under totality with our radar, because we can see most of the northeast US with this thing, and actually really eastern seaboard of the US. For the most part, we're getting some stuff in Florida that we can get to. We'll be in really good shape again for the eclipse, because we're going to be basically right on it. And then with going back to TEC, we sometimes do things like kilograms, and what they sort of did here is they took all of the and they essentially did a kilogram here where you took the differential TEC, so the change in TEC day to day, and they've essentially created this nice long line where they have the longitude. So the longitude of the eclipse as it goes through, you sort of cross plotted everything onto this longitude grid, and then also as your UT hours, you can see the big drop in TEC in the middle, and that line right there was where totality should be across the US. So again, when you look at sort of the the vertical TEC count, you're seeing sort of these big drops in TEC across. So this is just sort of that integrated TEC measurement over the whole time. You're seeing the drop. In some areas, you're getting about a max of about 40% change. So much larger than slightly larger than what has been modeled. And then here's just another look at sort of that same but percent difference, and you're seeing such a very big drop across here. You're even seeing some things where it's getting near 50%. So again we're the I don't want to. The modeling community is trying to understand why this is happening. There's a lot of questions as to why we're seeing these big changes, these changes that are larger than, say, what the models are saying. So I'm going to get to that in a minute. The other aspect that happens is that when you have these supersonic eclipse, the eclipse is actually moving. The shadow of the moon is actually moving supersonic with respect to the ionosphere. So what's happening here is you're actually seeing all kinds of very interesting shock waves that are coming through here. So I'm going to play this a few times because there's a lot of information within this one movie. So first off, I want to point out, as you go to the Rocky Mountains, you almost see something along the lines of like a reflection, a wavefront reflection happening from the Rocky Mountains as this goes over. The other thing that sort of happens as you go, you can kind of see how you have a wave function that's behind it, and it's becoming almost conical as it gets closer and closer to the southeastern United States. So we're seeing these really interesting wave patterns because they're moving very, the thought is that they're moving so fast through, it's almost like a shock wave, and you see like a nose cone of a jet going through, and you see sort of like a sonic boom happening. But again, since the shadow itself is the shadow itself isn't really a thing, but the effect it's having is actually very similar to what you would see sort of someone moving very supersonic through this. So just to show that one last time, and again, you're seeing all kinds of different wave modes and all kinds of ionospheric disturbances that are also happening in the background of this. So we have to also tease out things like TIDs from this as well. So a lot, but in the end, we see a lot of interesting stuff happening, and for some reason this made it go again. We're gonna watch it one more time, and then so yeah. So measurement results, comparing it, we have a greater drop than what was originally proposed that would happen with these. So that's kind of some of the big scale things I want to get out. If you go to these papers, these kind of, I think, go over, Coster mainly talks about, Coster et al. 2017 mainly talks about the comparison of the models versus the TEC. Huba talks about the 73 model that they've done, the ionosphere model. And then Shangrong Zhang's paper talks about the bow wave shock. Now, the bow wave shock was actually predicted in 1971 in a paper. So we kind of, we started to, we actually confirmed that sort of bow wave shock phenomena happening with this TEC data. So it was very interesting. So the whole of the measurement campaigns for the Eclipse of 2017 was very, very successful. Lots of new information was pulled out of it, lots of new ideas, and we confirmed some really interesting hypotheses here on things. So now, we're coming on the April 8th, 2024 eclipse. And that is going to be, we've had some time to kind of mull over our data and think about ways we can try to understand what's been happening in the data. So we start with, so for us at Haystack, we're very much about making new sensors, making new sensor techniques. Two techniques that we've been working on are new types of ionospheric sounders and a meteor wind radar we call Zephyr. Ryan had a really clever name because Zephyr is the Greek god of wind, I believe. So he didn't need to do an acronym. We always have these really terrible times trying to come up with names of our sensors. But Ryan had a good one, so he had a good one. But the aspects I want to just point out here is what they measure. And so we're going to be getting sort of a larger scale altitude with emphasis. We're going to be getting a larger scale set of altitude resolved electron density measurements. Now on top, and what Zephyr is going to add is going to be altitude resolved measurements of the thermospheric winds between about 80 kilometers and 120 kilometers. So back in the with some of the things that we believe was causing some of these inconsistencies between the model data and the modeling and the real data was likely due to changes in the thermosphere. Well, now we have a way to monitor the thermospheric change, or we're developing this method using the Zephyr meteor wind radar. So we're able to monitor thermospheric change plus a larger scale altitude resolved measurements of the bottom side of the ionosphere using emphasis. And we're going to do this sort of along the entire, along a good portion of the Northeast. And I'll show you our kind of plan later on. But the two sensors, so I'm just going to explain briefly what these two sensors are. So a meteor wind radar is actually, it's really an interesting topic. So the way I like to describe it to people is that we look at radars that look at meteors can measure winds in the mesosphere, and everyone's just sort of like, wait, you skipped a bit. I did. So what's happening is as we have meteorites hitting the Earth or entering Earth's atmosphere all the time. We often have very small meteorites in the order of millimeters just entering in. Now, when these enter in, they have a lot of energy because again, they're burning up the atmosphere because of all the friction. Now they create a wake of plasma. Now, as they kind of settle, the wake of plasma ends up moving in the directions of the mesospheric winds, because that's where most of them start to burn up. So then if you get this sort of a view of you get sort of a line of sight Doppler measurement of the plasma. So you're able to get a measurement of just the Doppler, the speed of the winds at that point. Now, your orientation of your radar sensor, you have to be sort of like right on you have to get a really good reflection of your radar system to get the wind, to get the measurement of the meteor. But that's where you use a technique called multiple input, multiple output, MIMO, systems where you put multiple transmitters and multiple receivers out. So you can get that angle diversity in order to see all the various winds and all the meteors measuring all the winds in all these different directions. And if and you need to come up with a method then to combine all that data in a coherent way. So and so Ryan uses some very interesting Bayesian inference algorithms to do such a thing. So this is the basic concept behind the meteor wind radar. We're just kind of expanding it and making it larger, because as you do multi-static these wind measurements, as I said, you get more information for each of the radar meteor head echoes that goes by. And so you get kind of a combinatorial number of transmit and receive links as it goes up. So, but the more so the more radars you put out there, the more detections you get more unique quantified measurements of the Doppler shifts, and you combine it and make a 3D wind field. And so you can get something here along these wind fields here. This is over Germany actually, because we have Kongsborn, they have a whole meteor wind network there. And you're able to get your meteor radar network gets you something on the order of 25 kilometers horizontal resolution, 2 kilometers vertical resolution, and you have a 30-minute time resolution. It takes time to kind of build up the number of statistics from the winds, but beforehand we had no sorts of measurements in this area. It's very tough to get measurements in that region of around 80 to 120 kilometers. But now we're able to actually do this sort of neutral measurement of the neutral spectra going through. And here you can kind of see, just sort of the different types of, wave and energy spectra that's coming through. You can see all the different momentum and energy flux within there. So this is getting, the meteor wind network is getting both, it's both getting horizontal wind speed and vertical wind speed as well. So you're able to get, all the different components of the wind up there. So that's sort of the very basics of how these meteor wind network works, and how Zephyr will be working coming next Eclipse. Now, ionospheric sounding is another technique. It's a very common technique that's been around. It's among the first types of remote sensing techniques. I think one of the things that happened was Marconi noticed that if he had if you bounce, he can bounce radio waves off of the ionosphere, and that's why they're called the E layer. And then the F layer, and then there's a D layer, and people aren't really creative. They just go by the alphabet. So they noticed this, and over time we figured out how as your radar, your frequency swept radar will monitor the index of refraction. And your index of refraction is basically parameterized by your electron density. So you can back out your electron density if you know what frequency you reflect at. This is vertical ionospheric sounding. It becomes much more complicated. You get a much larger change in the index of refraction once you go to oblique sounding, because you have to start taking into account magnetic field of the Earth and other and collision frequencies here. So this becomes much more complicated, but it is trackable to a certain extent. You just have to kind of work out the math and do if this becomes a much larger inverse problem that it can be tough to solve. One of the things with emphasis that's coming up is that we're going to have vector sensors, and we're going to be using MIMO networks. So we're going to get much more, much greater sort of coverage in frequency space, spatial variability, and we're doing something. Usually ionosons, they're much more power hungry. Generally, they put out on the order of about 40 watts for each pulse to kind of get your measurement. We're advertising something along the lines of about a watt for our system. We're doing actually a CW. We're CW, so when I say it's continuous wave. So instead of a single pulse, it's going to be a longer CW system. We're going to then match filter that to get out get the coding gain that we need. And so it's going to take a little bit longer than these larger systems, but we're going to have a much smaller power envelope. And the other aspect that makes that very useful for us is that we don't have as much challenge to license that band or license the frequency bands that we're going to be transmitting over. So our system is going to be much more smaller instead of these massive towers that cover a whole acre. We're going to have transmitter and then a single receiver that it'll be something around the size of, we call our atom antenna, but you have a loop antenna that's about the size of maybe a meter, 2 meters. And from there, you can do your transmit with your loop antenna, your vector sensor for receiving, and you're able to get, a measurement, an angle of arrival measurement of these things. So you can start doing things like inversion to doing imaging of the ionosphere, or the bottom side ionosphere. So this is something like I'm working on, very excited to be working on, and I've been working on it for about a little less than a year now. To try to get this together, but we're already doing this big, we've already shown these techniques to work in other programs. It's really just a combination of different techniques that we're bringing here. So we're looking something along the lines of, with their vector sensor ionoson, getting different type, we're getting the electron density and and ion velocity. So and we're sort of looking at something on the order of 2 to 10 kilometers vertical resolution. This is dependent on your bandwidth and how much bandwidth you put out. There are physical limitations for the system we're looking at, because we're using loop antennas for our first set of systems, but the loop antennas, they have a thing called Q that you have to deal with, so they can only transmit so much bandwidth at one time at really any efficiency. And so as you go lower in frequency, these loop antennas actually you can't actually put out as a larger bandwidth and get the same amount of energy transferred from your radio to the antenna and then out into space. So we're sort of looking at different ways of doing different, so if you want to have more bandwidth, you do a larger loop antenna or a larger dipole antenna. But for our angular resolution, we're going to get something along the order of about 25 to 50 kilometers of horizontal resolution and about 1 to 10 minute time resolution. So we're able to do measurements, over 1 whole minute and get profiles of the ionosphere. And then the other aspect is you have multiple polarizations that come out of these. So the way that things conduct, things will move through the ionosphere, can be dependent on polarization. So we have to split modes. Often you have to add extra antennas in your receiver. Well, you have to have multiple loops in your receiver to do that. We're sort of lucky in that the vector sensor itself does polarimetry naturally by itself. So we can just do that polarimetry right away. And for our transmit systems, we're actually going to have 2 orthogonal loops together, and they're going to be sending out codes, but coded waveforms. Now you can create waveforms that are orthogonal to one another. And so each waveform is going to be, within one loop versus another loop are going to be orthogonal to one another. But each one of these signals we send out can be orthogonal together by choosing pseudo-random codes. So we're going to be working on that. So this way, each transmitter and receiver, or each transmitter has sort of its own kind of coded waveform to it. So we understand, like, okay, if I apply a match filtering filter kernel to this, I'm going to then pull out the signal from transmitter A or transmitter B, just by changing what filter kernel you're using for your match filter algorithm. So those are the 2 systems we're sort of at the moment working on developing. Now, this is all coming together in again another big Eclipse campaign. And I'm going to talk about our operational filter and sort of the new ARC deployment for the new network, and some of what we're doing. So the network. So for this Eclipse, the background, we can see sort of I have here on this plot, a number of different eclipses. So you have the August 2017 one, April 8th. There's also an eclipse going on 14th of October this year. But it's only, I believe it's only annular. But what we're doing here is we're doing to kind of improve things, we're going to be doing things like expansion of our GNSS network. Right now, Millstone Hill, we're getting ready to do we're going to try to do a long-term collect, which means that we're actually gonna have the radar on continuously for a number of days. So you get a really nice comparison between days before the eclipse, days after the eclipse. We only recently were able to get to this capability because you require a number of technicians to be at the radar because it's putting out 2 megawatts of energy and you want to make sure someone's there to turn the thing off if things go wrong. Here in the upper right hand corner, you're seeing Millstone Hill field of view or the different. So what we're probably likely going to be doing is along that I believe on that red line we'll have we'll be doing different sorts of slices through this, along the northern part, and also have the zenith antenna looking fully, vertical. And that's kind of the basic type of observations we're going to be doing with the ISR. We're going to be doing an expansion of the GNSS network. We already have GNSS receivers from throughout the US, like as you saw before, making that big, large image. But you do want to sometimes take more and more stuff that you want to try to just fill in gaps that are there. So we'll be doing things such as placing GNSS receivers along, for example, for the October eclipse, be around White Sands Missile Range. We'll be placing some extra GPS receivers to get more GPS TDC measurements, GNSS measurements. And then also for the eclipse in, for next April, we'll be putting more along the line of totality as well to get even more measurements. So, so for us, and so that's I'm calling that the traditional sensors. For us, Ryan and I have a bit of a different sort of issue ahead. One thing we're doing is not only are we trying to measure this eclipse, but we also want to show that our systems work, that we're getting good measurements out of it. So we need a bedrock sensor, and we have one. It's the Millstone Hill Incoherent scatter radar. So what we've done is we've tried to create a set of points around the Millstone Hill Incoherent scatter radar, which is the red dot right there. And we've placed it along various relay triangles. Relay triangles are just a distribution of interferometric sensors that has various good sampling properties. And so we started with relay triangles as a way to sort of distribute things. And you guys, you came up in this corner here, so that's why I'm here. So we're distributing these sensors around. We're currently in the stage of doing RFI and site surveys to understand what challenges we would have to have, what challenges we have when we're putting out these sensors, and to make sure that we can see more of it. Now we may try to go further north to try to get maybe something in totality. But right now we're focusing on those sets of sensors, those yellow dots right now in various places. And we're going to again be doing site surveys. Below that, and unfortunately it cut off, we are going to be looking into Martha's Vineyard as a possible site. So you want to have a diversity of various baselines, so how far away things are from each other, to kind of get a better picture of what's going on. So yes, we're going to be creating these. We're going to be setting this network up relatively soon. Now, this is something that I should have mentioned in here earlier, but talk about the vector sensor. So a vector sensor receiver. So when you're usually using an antenna, you're generally only, we all know with our electromagnetic fields we have three E components, three B components. Antennas generally only get maybe one or two of those components. If say you have a cross dipole, for example, cross dipoles get polarization information. And so that's part of one of the things you can tease out of an electromagnetic an electromagnetic wave. But if you have all the components of the electromagnetic wave at a single phase center, you actually get a lot of information. You're able to do really fun things like angle of arrival measurement. So before, if you want angle of arrival measurement, you have to use phased arrays. Phased arrays, they have to be at least 1/2 wavelength away, otherwise you get grading waves. You create ambiguity in that. And with HF systems, if you want to have that, you're going to have massively long phased array systems. You're going to be way far away, and you're not able to. And so that's why, you see so much land, like you require a large amount of land to do things like the usual ionospheric. But with these vector sensors, you now have a compact antenna system that can get you angle of arrival measurement. So we can use it to get some basic angle of arrival measurement because we put in 3 dipoles and 3 loops, and you balance them out and try to make sure reduce the amount of mutual coupling. This sort of thing came out of a number of programs, Haystack, where we collaborate with Lincoln Laboratory, the Aerovista deployed antenna. This is a small satellite that will have a vector sensor antenna that is going to be sandwiched in there and then deploy out. And that's going to be used to study the HF environment and look at various types of auroral radiation that are coming along the magnetic field lines. And we've used these systems, we've gotten them to work, we've done things where we can do direction of arrival estimation of WWV, which is a simple antenna. We have this atom antenna that we've done in the past. So we're familiar with this. We have the ability to sort of do these measurements. So we have these vector sensors ready. So the next thing, we have to get our radios together. We're going to, for our software-defined radio, we're going to be using RFSoC. Niku has been working with the lightning interferometer network. So we're going to be using a similar board to what he's doing as our first sort of rev on this. We're going to need to develop a mixing board because this has 4 inputs to it. But it has a huge sampling bandwidth, something, I think it's like what, 5 gigasamples per second on the.
I think it's like 9 gigasamples.
9, okay, so it's very, so you're able to put up a lot. We do need to develop a mixing board, but we do have something we can base this off of. So and then your signal processing can be done through the PIN framework. These RFSoC boards, they're about $2,500 each. So it's actually it's a rather good price, but they are a bit power hungry, around 45 watts. We were hoping to use the Aurora board, which was the radio that was going to be used for Aerovista. And just it's far too expensive right now for what we need right now. Unfortunately, our second rev will be using that Aurora board because the Aurora board runs at about 20 watts, under 20 watts. So and with that mixing board in there, might be another few more watts. So we're seeing a difference of about 30 watts of power of one SDR versus another. But that's like a highly integrated, specialized software-defined radio for HF. And so that's why it's got so much lower power requirement. Here's sort of a receive system, the overall receive system. You'll see on the bottom right is sort of the whole battery and EMI filters. These were derived from Franklin's Rapid project. Franklin developed an incredibly quiet radio called Rapid radio array of portable interferometric devices. It was so radio quiet that they kept, at one point they were testing it and they were seeing this weird ephemeral signal go in. It took them a little while to realize it was their mouse. With this, we're gonna have our vector sensor channels, your RFS, across RFSoC, spread across 2 RFSoC channels. We're gonna be using the Jetson Orin Nano. This is a little NVIDIA signal board computer that has a GPU in it. We're working out the specific one. You know, this will allow, one thing that we're gonna see ourselves doing is we're gonna be doing a lot of correlation type of operations to do the match filtering. So having a GPU that you can program to do 1 million correlations, or a whole, no, not 1 million, but a whole bunch of in parallel, can actually give us a really capability in order to see everything. And then it's going to be within a number of, you know, we're going to have a 5G antenna. Frank also is working on, one thing we do at Haystack, we combine a lot of like campaigns in one project. So we can do a lot of stuff. He's doing he's a PI of a project called Swift, which is about spectrum sensing. So he's developing ways to do spectrum sensing with this as well. So he has 4 input channels to these. There's 4 input channels to RFSOC. 2 are going to be for our vector sensors, and he's going to have 2 channels for his various spectrum sensing things he wants to do. Because, you know, he was nice enough to help put it together, so he's going to do something with it. But this is the receive system. The receive system is by far more complicated. The 2 transmit systems are a bit simpler. We are going to have, so we're going to have about 10 RX sites, 10 low power transmitters. So the low power transmitters are the emphasis transmitters. Those will be emitting something on the order of like 5 watts at one time. And the high power is going to be on the order of about 500 watts. So that's the meteor wind radar. Now it's the meteor wind radar in a single frequency channel. So you need that power because you're looking at such small specular reflections. And so the RX, so we're going to have cross dipole antennas, and then not cross dipole, cross loop antennas, and then various cross dipole antennas for that one. And then we have for the RX site, the vector sensor antennas. And we're going to be putting them in, we call them Mahali enclosures. Mahali was a program to do low-cost GPS receivers in an enclosure that could deal with things like, you know, the Alaskan winter. So we're sort of leaning on experience from former projects to kind of really put this all together. So that's our crazy idea for looking at the eclipse. And so for Summery, you know, we're really excited because again, it gives us atmospheric scientists, a really natural experiment to see this. Now, I didn't cover what modelers have sort of released at the moment, but we are working with them to sort of, you know, again, get, you know, our physical measurements closer to what our modeled, you know, will be. So, you know, this is how science works, where you know, we have our observers, you know, like myself, and then we have you know, Joe Shuba, who are modeling and doing the theoretical underpinning of what's going on, trying to understand theoretical underpinning. We get 2 new types of radars to study the ionosphere and thermosphere, and we'll be deploying these things for the 2024 eclipse. Probably this fall we'll have a hardware and putting it out there, and you know, we're also up for talking with other people about the eclipse and what sort of work can be done. We are Anthea Coster at Haystack is currently trying to put up more GPS receivers. So if you want to work with her on that, she's more than open to work with people on that. We actually have a number of GPS receivers we're going to field and possibly creating real-time capability for that. So that's you guys. And then also I want to thank all of the other people at Haystack for giving me slides to put this together and show that we all sort of help each other out to kind of you know, kind of spread our research. So and yeah, so that's what I have. Thank you for listening.
Are there any questions for speaker?
In-person question, maybe first.
The GPS receivers, are they really specialized, or you know, are they simple as a phone?
There's like, so the phones are getting better. So you need dual frequency GPS.
Right.
Generally, your phones don't have dual frequency chips. Only I think now we're starting to see dual frequency out there. And then you have to deal with the programming the phone has and dealing with that. That then takes a lot of time and energy to kind of find someone who can do that sort of software development. There were experiences before trying to do the phone-based GPS, but you know, again, you get into Android or Apple's ecosystem, and you need someone who's specialized with that. And then they're like, well, I could be doing this, or I can be making apps, and, you know.
Someday, maybe.
Honestly, you find the right student, you probably can get it out of a good, computer science student, and for a master's project maybe, or a PhD project even. Well, if you want to do a PhD project, you're gonna have someone who was like, I was doing app development, now I want to do science, and then you find that one person, you're like, yes.
Any other questions?
Yeah, just wondering what you're doing to collaborate with other assets, I guess, is the thing, for example, Cosmic Two. I know there's a founding rocket planning to be launched, and who knows what else.
Yeah, so the August 2023 eclipse, there is actually sounding rocket going up to Wismere, and we are actually collaborating with them. So we're gonna have some stuff, so that we're collaborating in that end with it. I haven't heard anything about any other sounding rocket campaigns for the April 2024 eclipse, I assume.
It's the same guy. I mean.
Oh, is it what's a row, yeah. So is he going out of Wismere both times, or is he going Falls, yeah. So we'll be talking with him and probably working with him. We're gonna be, we were going to do, he wanted actually a lot more coverage for both campaigns, but we just weren't in the right, we weren't in the right development cycle to get it for the August one, so. But we will have something for April. We're going to be working with him, probably sharing data with him, and he'll be sharing data. We'll put a lot of data online, basically, in Magical.
And what about Cosmic Two?
I haven't heard anyone from I haven't met anyone from Cosmic 2. I'm gonna rely on my colleagues at Haystack who might know them. Probably Anti-Coster is probably better plugged in than I am.
I mean, probably the key question is e-region retrieval, whether they incredible e-region retrieval. So
Yeah.
Questions? What about the online audience?
I don't think there's any question online.
Okay, I have a question. So, for the vector field sensor, you have 6 components, right? And then you need 6 channels, but for us, so over to, so you only allocated 2 channels?
No, well, so we have two channels. What we're gonna do is we're going to be looking at a bandwidth limited set of signals. So something like, we're gonna be looking from like 0 hertz to like maybe to maybe 50 megahertz. And then what we're gonna do then is we'll have an analog modulation chip that'll just spread them across the frequency space of those channels. So one channel will be for all of the E, one channel will be for all of the B's.
Okay.
And so we're gonna be taking all those channels and spreading across frequency. So we're kind of multiplexing in a slightly different way.
Okay, so then for so you show this map and then UH or Durham is represented by a dot, right? So at this dot, what sensor or transmitter you're gonna install is one HF transmitter, one reader, HF reader or receiver.
And we're gonna do one transmitter, the low power transmitter, and one receiver. We're going to go through FCC. We actually are going to do all the FCC requirements too. So we have basically our template FCC license that we're then gonna populate with address, this and that, and location. So we have all this sort of like templated out, and then when we have the site selected, it's going to be get them all to the FCC as soon as possible. Because they can take their time. Although lately, I don't know, Franklin had an experience where like he sent in an application for a license and a month later he got it. He was like, what? So I don't know, maybe things changed.
Okay. And also vector field sensor, right?
Yes, we vector field sensor out there. And so we'll have that out from probably have the physical system out there, probably beginning in the fall before the snow hits.
Okay.
And then we'll be, I'll probably be working on specific processing pipeline software, and then when the Eclipse, and then between March and the end of May. March and May, we're gonna give ourselves like 2 full months around the Eclipse. So it's the beginning of March, beginning of May, and we're gonna have 2 months around the Eclipse, so we get data where it's like, okay, we know that our vector sensor systems are working, we're getting good electron density measurements. We can see, with the thermospheric winds, we're seeing, reasonable correspondence, say with the ISR, for example. So with thermospheric winds, you can kind of get some ideas of the lower, some of the lower winds in the ionosphere. So when you get really low in the ionosphere, the ions and neutrals are coupled together. So you kind of get something that's kind of like a measurement of winds, but it's not completely 1-to-1. Plus, also the ISR is only looking in one direction. So we're gonna have to be very careful, kind of, okay, we got one going in this direction. Okay, now we got the ISR and the vector sensor. Meteor wind network is in the right direction. Then we're also be doing this with the electron density. So it's going to be, we're going to make sure that we have enough data of quiet time, quote unquote, during these buffer months.
Good. Any other questions?
I was just wondering if we have a geomagnetic storm just before the day. And
Don't say
I'm just wondering how to compare that. This is kind of.
Yeah, then it kind of ruins your experiment. And
Does it work totally that?
I don't think it'll totally ruin. We'll learn a lot, but again, you're always going to have these questions of what is a geomagnetic storm happening. And again, it will just create kind of some people who there are various researchers that have very specific theories that they want to show because they did maybe modeling or whatever. Maybe something's named after them. And if it's like not happening, then it makes them feel bad probably. But we're humans. This is just something. And if say you see something happening and there's a geomagnetic storm happening at the same time, how do you disambiguate the two? Now there are some things maybe that you can say, well, that's a geomagnetic storm effect because that would never happen based off of this. But but there's also this other aspect. When you're looking at data, you're sort of looking at a projection of things, and you're seeing these different, if you saw in the video of the TEC during the eclipse, you're seeing all these different wavefronts, and you can argue like, well, that wavefront looks like this. Well, it could be, it could be this orientation. One good thing though about like maybe the vector sensor sounder is, well, we're getting sort of more information, so we're not getting as we're getting much more information in our projection, so we'll be able, maybe we can, beat some arguments down of saying like, well, if we can altitude resolve some wave fronts going through and say like, well, this wavefront was this orientation, which sort of, begets this one type of phenomena versus another. Yeah. So that can help again disambiguate various phenomena.
Yeah, but it's challenging. Right?
It's always challenging. Yeah. It's going to be very important to do that sort of disambiguation and try to, look at all these different data sets. And now we're in such a period where we have so much information. You have to be very careful about how you kind of sort and correlate all these things.
Yeah, so also worse, I think, for see changes in geomagnetic field to the eclipse, right?
We see changes?
Yeah, actually, you can see that changes, but due to the currents on the ionosphere, you can really correlate changes on the geomagnetic field to the currents on the.
Can we?
Yeah.
Oh.
So this is an interesting thing.
Yeah.
Right. So, but maybe see you have like more electron density on the ionosphere, see how the change is on the currents that generates those diurnal changes on the geomagnetic field could be interesting.
There are some. These are going to be a lot of questions that we're going to ask. You're familiar with our Madrigal repository?
I heard of it.
Yeah, so we have a lot of this data up on Madrigal, and it's going to be, for us, our big thing is going to be getting is we're going to try to get as much good measurement data. So, again, you get your measurement, your electron density, and you're going to get some error bars around it, and you're going to have sort of the resolution that you kind of use to kind of figure out, okay, and then you can combine it with the other data sets to know that, okay, at least, here's a reasonable approximation of what's happening. Here's the information I need to kind of understand what's going on. I would really highly suggest looking into Madrigal. Also, the information in all of those. There's usually like a write-up that each of the PIs for each sensor puts up there, and it's had a wealth of information about how the sensors work, and also maybe some things you might want to realize that's going on before you put your paper out. Good idea to read it, because you might like notice something like, oh, that thing I looked at, and it's because of this. Okay, that's that instrument effect. That's noted in there. that can, it happens to everyone. It's always tough. Again, there's a lot of stuff happening in these complicated systems.
Any other questions? Now, let's have a speaker, yeah?
Thank you everyone for joining and see you next week and this time for graduate student seminars.